and the, and the MS and PhD degrees in electrical engineering from the University of Connecticut. He is currently serving as professor and chair of the Department of Electrical Engineering and Computer Science at the University of Missouri. His research interests include semiconductor devices, nanotechnology, biomicroelectronics, and monolithic sensors. He has more than 100 publications in refereed journals, more than 150 papers in conference proceedings, and a number of invited talks. He also co-authored a book and 12 book chapters. Prior to joining the Department of Electrical Engineering and Computer Science at the University of Missouri in July 18, he served as James W. McConnell Professor and Associate Head of the Department of Electrical Engineering and Computer Science of the University of Tennessee. So we successfully recruited him here. In recognition of his teaching, research, and related effort at the University of Tennessee, he received the John W. Fisher Professorship, Eta Kappa New Outstanding Teacher Award, Moses E. and Manning Books Distinguished Professor Award, College of Engineering Research Fellow Award, the Gonzalez Family Award for Excellence in Teaching, Tico College of Engineering Teaching Fellow, University of Tennessee Citation for Research and Creative Achievement, Electrical and Computer Engineering Faculty of the Year Award, and the Alexander Prize. He also received Outstanding Electrical Engineering Professor Award at the University of Missouri. And I'm very proud to say that we became not deep friends yet, but close friends over the past few years. And it was immense pleasure that I bring you Dr. Islam to his presentation.
Thank you, Dr. Simoes. Dr. Simoes, for your kind introduction. So I'm going to share the screen, I believe.
It's already shared.
It's already shared? Okay, so let me go to my slides. Okay. So today I'm going to be talking about sensors, edge AI, and deep learning for personalized diabetes care. I'd like to acknowledge my former PhD student, Maruf Hussain Shubo, who did most of the work that I'm presenting today. He recently completed his PhD and will become an assistant professor in the Department of Electrical and Computer Engineering at University of Texas, El Paso in August. So AI market from 2023 to 2030 is projected to grow from $150 billion to more than $1.3 trillion. The key enabling technology involve deep learning methods. And the next frontier of this AI is to bring artificial intelligence to edge computing, which you call edge AI. Now, those of you who are familiar with edge device is that it's the endpoint of a network. It is between the data center and the real world. According to IBM, the definition of edge AI is the deployment of AI algorithms and AI models directly on local edge devices such as sensors and IoTs, which enable real-time data processing and analysis without constant reliance on cloud infrastructure. Deep learning mimics interconnected brain neurons learning from data. And in this view graph, we are showing there are two processes of deep learning. One is training, the other one is inference. Training involves the forward and backward propagation of data through an iterative learning process. And inference uses a trained model to calculate an output from a given input in the forward propagation process. So this is the process is automatic learning, it acquires automatic feature learning, and it improves performance with increasing layers. In this schematic, we are showing input layer, output layer. These are the input layers, output layer, and there are 3 hidden layers in here. And all the dots are neurons. So if you increase the layers, then the system becomes more efficient and accurate, but then it also increases the computational complexity. For edge AI, we take the data set, process it, and train a neural network model. Then we do the inference on an edge device, such as smartphone, FPGA, application-specific IC, or microcontrollers. There are 3 types of inference we can do in deep learning. One is the inference on edge, like edge devices, inference on server or cloud, and there is another one we call collaborative inference. 80% of the inference will be on edge for edge AI, which produce smarter and faster decision, and it also assure enhanced privacy and security. AI is everywhere, and there are a large number of applications of AI. Some of the applications that we are interested in are healthcare, financial services, industrial maintenance, transportation. In my lab, we are interested in applied AI, which includes machine learning and deep learning to solve real-world problems to bring AI benefits to users. The next generation of personalized care at home or personalized home care involves, there are several different networks such as wireless body area network or medical body area network, which will collect the data according to physician specification, and then will process the data and provide some output. These include remote device control, medicine reminders, object location, and emergency communication. In our lab, we are interested in working in the personalized home care, and we are focused on two types of devices. One is to diagnose and manage diabetes. The other one is to monitor sleep apnea. So in today's talk, we'll be focused on diabetes. Diabetes is a chronic metabolic disease. According to International Diabetes Foundation, or IDF, there are 10.3 million deaths worldwide. And by 2045, the forecast will be 783 million adults will have diabetes. The global economic burden is the healthcare expenditures right now is going to be, in 2023 alone, was $1.3 trillion. According to CDC report in US, 37.3 million people have diabetes, which is roughly 1 in 10. And 1 out of 5 of this population, they are not aware of having diabetes, and which is now the 8th leading cause of death in the United States. So without effective prevention or diagnosis and management, diabetes epidemic will continue to rise. There are several reasons for the rise in diabetes. One is the existing diabetes management system. These systems lack early stage evaluation, so the opportunities for early interventions are usually missed. There are manual diagnoses which are prone to errors and inconsistencies, and it also impact accuracy and reliability. There is also expert-dependent diagnosis, which relies on experts, which are more accurate and reliable, but access is very limited. Most of the time, when the diabetes is diagnosed, is in the presence for another health condition, which can complicate due to late detection of diabetes. The consequences are prolonged unawareness, health deterioration, and ineffective self-management. There are a couple of potential solutions that we are looking into. One is the ML or machine learning embedded smartphone application for early stage diabetes risk assessment, which I'm going to present some of our work today, or an ML embedded portable medical device for automatic diabetes detection. This work is involving a smartphone application for diabetes risk assessment. So objective is to build accurate and reliable machine learning model to predict diabetes risk at early stage, and to integrate machine learning in edge and user platform. So this is showing us the schematic of our system. We'll acquire data and build a machine learning model, train and cross-validate the model, evaluate performance, and then do grid search. Grid search is hyperparameter tuning technique used in machine learning to find best combination of hyperparameters for a given model. Hyperparameters are variables that are not learned by the model, but rather set by the user before training. Then this model will be inferred on or inferenced on a AI device or AI edge device for AI on edge, and the data will be taken as an input from questions and answers from the subjects, and the model will predict whether this individual is at high risk or low risk depending on the answers. So the dataset used for this work was obtained from UCI, University of California, Irvine Machine Learning Repository. There were a total of 520 subjects, 328 of those males and 192 females. And there were 16 attributes that includes age, sex, sudden weight loss, weakness, itching, delayed healing, muscle stiffness, and obesity. Polyuria, polydipsia, polyphagia, genital thrust, visual blurring, irritability, partial paresis, and alopecia. Among the 520 samples, 200 were healthy and 320 were diabetic. So 75% of the data was used for training and 25% was used for testing. And we applied tenfold cross-validation to obtain the best suited model. The output of the system is binary, either it will be diabetic or non-diabetic. Different types of machine learning models were used in this work, including logistic regression, naive Bayes, support vector classifier, multi-level perceptron, random forest. And this table shows the accuracy, specificity, sensitivity, and F1 scores for various machine learning models. You can see based on our analysis, we found that random forest will provide the highest accuracy, specificity, sensitivity, and F1 score. So we applied or deployed random forest model and trained it into an Android app. This is showing the schematic of this work, which includes questionnaires are obtained from the subjects, and they are being used to assess the risk of diabetes. So this is showing us the smartphone application that we have. So there has to be, I'm sorry. Let me go back to this one. Okay.
It's no longer shared.
Okay. Okay. It's not shared. Okay. I'm sorry. It's a technical problem. Can you see it now?
Yep.
Okay. So let me go back to the beginning.
Yeah, it's moving up. It's beginning to show.
Okay. So,
It stopped. That's why.
okay. Now it's going. Yeah.
Yeah.
Oops. Every time I move this one, it goes out. Okay. So let me leave it as it is. And you can see
Yeah.
start with question on age.
Gender.
So you can see that this smartphone application actually provides an initial risk assessment of diabetes. It doesn't require any complex clinical measurement. It can be done anywhere, anytime, and it can maintain privacy security because the decisions are made offline and the screening process is quite fast. So this was our initial work on this diabetes prediction model. And then in addition to this one, we've been working on biomedical sensor technologies for several years in my lab. We work on both wearable and implantable sensors. The implantable sensors are for glucose detection or diabetes prediction. And these are implantable, meaning that the sensor can be inserted inside the body with minimal invasive process.
Frozen.
So the motivation for implantable sensor involves diabetes care. Currently, we use the blood glucose test using finger pricking and keeping records, and then based on the data, then the insulin pump is deployed. There are other devices that we have in the market called Freestyle Libra, which is basically an insulin pump which can measure the glucose level, and if the glucose level is very high, it can actually insert insulin into the body. But the test strips are not reliably usable, cannot be used for continuous glucose monitoring, and there is the continuous in vivo closed loop monitoring is not matured enough. So we developed an implantable glucose sensor, and this is the circuit that my students and I have designed in my lab in Tennessee. This is a integrated circuit or CMOS chip, or we call microchip, that we designed. That's 1 millimeter wide and 5 millimeter long. And this is the aspect ratio is such that we can actually insert this whole device inside the body with minimal invasive process. The integrated circuit or the circuits on the chip will require power. And to get power, we put photocell post-processing. And when the laser light is shined on this device, it will activate the electronics and will start recording the data. The glucose sensor in this case was commercial platinum electrode that were added to the tip of this sensor. And the whole thing is put in a biocompatible package and can be introduced inside the body. We developed this work a few years ago, and this chip that we did actually can do more than just the glucose. It can do glucose, lactate, oxygen, and pH. Now, this device is being currently under testing in animals at the University of Connecticut, where I actually did my PhD. And that group is currently testing on animals. And hopefully soon there will be clinical tests for human. But the biggest challenge in this work is that we are getting individual levels of glucose, lactate, oxygen, and pH, but we don't have a model currently to correlate all of those measured parameters into a glucose detection model. So that's the work that we would like to continue in the future. In addition to commercial glucose sensors, which are platinum electrodes, we also tried biocompatible carbon nanofiber-based sensors. We developed those biocompatible carbon nanofiber sensors at Oak Ridge National Lab Center for Nanophase Materials Science. We got some grant to work on it. And that sensor actually uses enzyme wiring or co-immobilization of glucose oxidase and horse radius peroxidase on the surface of VSANF. And when you apply some potential, then glucose is oxidized, and oxidation of glucose results in hydrogen peroxide and carbon dioxide. Then hydrogen peroxide reduces to electrons and water, and that electron or ions are actually measured by our sensors. So we tested the sensor with various levels of glucose, and you can see after about 15 seconds, we get different levels of current for different levels of glucose. And when we took this data and plotted, we got an R square of 0.998, which tells us that the sensor is highly linear. We also tested this device in presence of other interfering agents, because in blood, we not only have glucose, we have other interfering agents. So our testing involved interfering agents such as uric acid, acetaminophen, and also ascorbic acid. And in presence of those interfering agents, we would notice that we can still detect glucose. Every time glucose is added to this solution, we can see a spike indicating that glucose was detected. This is the testing setup that we had in our lab for testing this device. The diagnosis of diabetes, their current diabetes method includes initial asymptomatic behavior, which we have provided some results on machine learning embedded smartphone application, which can determine when someone is a symptom of diabetes or not. Then there are home monitoring devices, which measures blood glucose and gives an indication of diabetes. There are hospital-based tests such as fasting plasma glucose, oral glucose tolerance test, and glycated hemoglobin. There are challenges that remain is that there is currently no medical device that can automatically detect diabetes. And obviously, like I described earlier, we have a lack of well-defined diagnostic relationship among physiological measurements. In our device that we designed for implantable glucose sensor, we do measure glucose, lactate, oxygen, and pH, but there is no well-defined relationship between them. that can predict the diabetic's behavior. The goal of our research is to develop and design a medical device capable of automatic detection of diabetes. We envision this device to be portable, can do real-time detection if affordable and accessible. And implementing this device in machine learning will provide us learned decision and provide high accuracy. So this work that I started with, this work, we collected data from PIMA Indian diabetes dataset. There are 8 different attributes in here, which includes pregnancy, blood glucose, blood pressure, skin thickness, insulin level, BMI, pedigree function, and age. And then we develop a deep learning model, which includes model training, parameter organization, and performance evaluation. Then we extracted model parameters in terms of weights and biases, and then we build the deep learning model for inferring on a hardware, and then we got the output. So the process begins with training and evaluation, which includes collecting and pre-processing of the data, and then training and validating machine learning models. Then we do model optimization and extraction, which includes implementing optimization techniques, validating optimized model, and extracting model parameters. Then we did the hardware design simulation, which include optimized model inferenced on digital hardware, and hardware optimization techniques were implemented. And we did performance analysis and resource utilization. And then at the end, we developed prototype. We realized it's on a field programmable gate array. Some of you are familiar with FPGA. That's a board which can be programmed to perform a certain function. So we have taken this model, implemented on FPGA, and tested. This is the deep learning model architecture that we implemented. This one has 8 attributes in the input, and there is an output layer, which is giving us a binary output of 1 and 0. 1 is diabetic and 0 is non-diabetic. And there are 3 hidden layers in this case. And each hidden layer has got a certain number of neurons. So we have taken the data set, PIMA Indian reservation data set, diabetic data set, and 75% of data was used for training the model, and 25% was used for testing. We applied RMS, prop, optimization, and binary cross entropy loss function, and then developed the best model for highest validation accuracy and minimum loss point. So this table shows different methods we employed, including logistic regression, decision tree, support vector machine, random forest, ML, fully, FNN, and DNN, and then our proposed fully connected neural network. And we compared them in terms of accuracy, precision, recall, and F1 scores. And as you can see, this fully connected neural network that we developed actually provides the highest accuracy, precision, recall, and F1 score. We realized this model on a hardware called field programmable gate array, or FPGA. We use RTX7 FPGA, use 8-bit integer values instead of floating point library. And then instead of multipliers, we use shifters. And we are showing here in this table on the left, bottom left, for this multiply accumulate operation, we utilize a large percentage of this hardware. Whereas if you only do shift operation, we only take 1/3 of the of the hardware utilization compared to multiply accumulate operation. So we use shifters in our hardware implementation. And then this is showing the test results of our hardware. And hardware is an FPGA, and then we have this output 7-segment display, which shows us 0 or 1 output. And we put this model in the computer, and they're using USB or UART, which stands for Universal Asynchronous Receive Transmit Standard, or Universal Serial Bus Standard. We input the data from computer into the hardware, which is the FPGA, and then we provide the results based on the input. So for this particular case, depending on the input, this individual is showing us an output of 1, meaning that this person is diabetic. So then what is the next step in our work? We would like to do edge AI for point of care diagnosis. such as diabetic risk assessment and automatic diabetes detection. So for diabetic risk assessment, we like to integrate activity and sleep tracking, and then population-specific data and risk factor to personalize our system. And then automatic diabetes detection can be implemented on a hardware or such as FPGA. But our target is to do application-specific machine learning chip. The problem with our diabetes model that we have so many parameters that the implementation of this of machine learning model on a chip will require a large chip area, and this will require funding. So we are working on proposals to get funding where we can actually get a bigger chip. It costs a lot of money to develop a chip, especially for pilot chip. And if we go for higher end process, then we can implement our model on a smaller chip, but higher end process also is quite expensive. They're running close to $100,000 for a prototype run. So we are waiting for big funding to be able to apply our machine learning model, implement our machine learning model on a single chip. For the type 1 diabetes, this is an autoimmune condition in which the body's immune system mistakenly targets insulin-producing beta cells for destruction, and which drastically reduces the ability of the body to produce insulin. Without insulin, the blood glucose concentration becomes too high, which is called hyperglycemia, which anywhere the BCG level higher than 180 milligram per deciliter, we categorize that condition as hyperglycemia. Hyperglycemia may cause long-term health issues if it is not addressed properly. Then when insulin is applied to the type 1 diabetic patient, the insulin can cause the drop in the blood glucose concentration. And anytime the blood glucose concentration falls below 70 milligram per deciliter, which is categorized as hypoglycemia. Hypoglycemia can lead to serious health complication if it is not properly addressed. So the blood glucose prediction, this knowledge of glucose projection is crucial. First of all, if you have a personalized sensor collecting the data from a patient, and then we put this data into our machine learning model, which can accurately predict glucose prediction level, and then we do the intervention. So intervention involves optimal insulin dosage, meals, and exercise. And then we can also produce the algorithmic control of the closed-loop insulin delivery system like insulin pump, and then can also take preventive actions in advance to limit those adverse glycemic events. In this regard, we develop a deep multitask learning model, which includes 4 attributes of the input, which is the CGM, blood glucose concentration, carbohydrate, bolus insulin, and finger stick glucose. We had shared hidden layer, clustered hidden layers, and subject-specific layers. The advantage will be improved generalization, mitigating inter-subject variability, and we produce faster result because of the parallel learning and implicit attention mechanism. So this model was used to predict the glucose trajectory after a certain period of time. We call it prediction horizon. So prediction horizon 30 minutes means that 30 minutes later, what will be the blood glucose concentration? This model can predict for a prediction horizon of 30 minutes. And this is comparing with the experimental data, or we can reference measurement data. You can see for pH of 30 minutes, the projection list follows pretty closely the measurement references. Whereas as the projection horizon increases to 60 minutes to 90 minutes to 120 minutes, the simulation results actually deviate slightly from the measurement. So this was, we took one particular patient from PIMA Indian diabetes dataset, patient number 570 for 24 hours, and we looked at these glucose predicted values and the values that are obtained from measurement reference, and we can see that lower the projection horizon, the better results we get. This was also represented in Clark error grid for patient number 596. Clark error grid has 5 zones. Zone A is called the clinically accurate zone. Zone B is the benign zone. Zone C is the overcorrect zone. Zone D is called failure to detect, and zone E is erroneous. If our data falls in this A or B, then we are pretty accurate. So in this case, you can see for prediction horizon of 30 minutes, all the data is either in A zone or B zone. And as we increase the prediction horizon, some of the data will be falling into the other zones. So we can see, we can conclude that the increased prediction horizon, the predictions are more dispersed, and 94% are clinically safe predictions up to 120 minutes of prediction horizon. So what's next in our research? We can integrate predictive models with edge computing. And so one of the things we can do is to develop a model, and depending on the input, which could be desired blood glucose level, target window, and sensor data, and then their model will predict recommended amount of carbohydrates or bolus insulin that has to be deployed or applied to the patient. This is one of the work, and we also did some non-invasive diagnosis of diabetes using heart rate variability, which I'm going to present next. So biophysical mechanisms, autonomic nervous system and endocrine control can control cardiac rhythm. These systems regulate heart rate variability, which is the time interval between heartbeats. And any of the ailments in those systems will cause HRV fluctuation, which can impact cardiovascular adaptive capacity. Diabetes triggers cardiovascular autonomic neuropathy, or CAN, which is a life-threatening complication. And HRV is highly related to CAN and diabetes pathogenesis. So diabetes affects HRV, which also affects the results of the ECG, which results in dispersed QT, STT changes, can have sinus tachycardia and ventricular hypertrophy. So HRV can be used as a diagnosis tool for type 1 diabetics patient, because HRV captures these alterations of ECG effectively and can be utilized in type 1 diabetes diagnosis. So cardiovascular changes actually precede diabetic symptoms, and or determining the heart rate variability or analyzing heart rate variability, we can actually predict whether this individual have any kind of a symptom for diabetes. So this is the work that we have done on the HRV features using machine learning. The dataset used for this research was D1 NAMO dataset, which are ECG signals are obtained publicly available dataset. And then we use ECG signals for HRV feature calculation using different machine learning techniques such as AdaBoost, decision tree, K nearest neighbor, naive Bayes, random forest, XGBoost, and multi-level perceptron models. And then we tuned the model, and then we did the classification. And then there is one type of classification we show you in the next slide called ensemble classification. And for all those work, we use area under curve as the performance metric. Now, area under curve is the measure of the ability of a binary classifier to distinguish between classes and use as a summary of the receiver operating characteristic curve. This is showing you the schematic of the data collection process, data splitting and cross-validation process, and model building and research and performance evaluation process. This table shows that various HRV features, there are 8 of the HRV features, and then we compared with the T1D or type 1 diabetic patients and healthy subjects. As you can see from this table that the standard deviation for neural network interval, or called SDNN, for example, for T1D patients, it is 228 and fluctuates a large by about 200. And then for healthy subjects is 106.6, and it fluctuates by about 145. So all of those features are plotted in these right-hand plots, and you can see 0 stands for healthy patients and 1 for diabetic patients. You can see there is a clear demarcation between healthy and diabetic patients. So the statistical parameters and probability distributions actually give us a clear differentiation between healthy subjects and T1D patients. There is a distinct distribution of HIV features are observed in case of healthy and T1D patients. And it's a strong indication that HIV features hold promise for the type 1 diabetes detection. So we also compared different machine learning models, and we calculated AUC, accuracy, and precision for each of those models. You can see the K nearest neighbor model gives us the best area under curve, and for random forest provides the highest accuracy and precision. We also ensembled the model, meaning that we have different models. So for example, in here, we added different models, and then we studied their AUC and accuracy. And we found that AB plus XP, if we ensemble them, then we get the best area under the curve. And combining these DT, Canon, NB, RF, and XP, we get the best accuracy and precision. So in summary, we based on the work that we had done, we can confirm the feasibility of using heart rate variability features from single lead ECG as a promising tool for non-invasive detection of type 1 diabetes. Our ongoing efforts in the lab include refining risk assessment. We are trying to incorporate wearable device that can track activity and sleep patterns and incorporate population-specific risk factors. We are trying to fuse ECG and PPG, which stands for photoplethysmography, which measures blood volume. We combine ECG and PPG signals for non-invasive diagnosis. We are trying to understand different comorbidities that related to diabetes, such as kidney disease and cardiovascular activities. We are also trying to do real-time monitoring with edge computing. So in summary, our lab, we are working on edge AI for point-of-care diagnosis, such includes early-stage diabetes risk assessment using smartphone application and automated diabetes detection. We also do deep learning for decision support, that is personalized blood glucose prediction, and then non-invasive diabetes diagnosis using heart rate variability. So this work was done in my lab, which is analog mixed signal VLSI and devices lab located in Naka Hall. And then my graduate student, Mohammad Maruf Hossain Shubo, he's completed his PhD and is going to be a faculty at the University of Texas in El Paso. And he will have a new lab called Edge and Biomedical Intelligence, or EBMI laboratory. So we will invite all of you who are attending today and those who are not attending today but are interested in collaborating with us. We are electrical engineers. We do engineering stuff, but we need data. And so the data that the data scientists that we have at this institution, if we can collaborate with them, we can probably do a outstanding work in terms of diabetes detection and prediction. So with that, I will leave it for further questions. Thank you.
Thank you. Thank you, Dr. Islam. Outstanding.